Today, we're diving into the incredible world of the Victoria Boliviana, the architect of the Amazon. This slide gives us a detailed look at its structural genius, showcasing how its design principles directly inspire biomimetic engineering. You can see various elements like the primary cantilever rib, the cross-bracing lattice, and the edge-reinforced upturn, all contributing to its immense strength. With a surface area built to withstand structural loads of up to 80 kilograms, this plant is a marvel of natural engineering, offering crucial insights for biomimetic design. Let's begin with the fascinating story of the new queen of the water. In 2022, a 177-year-old mystery was finally solved at Kew Gardens. Genetic analysis confirmed that what was previously mislabeled as Victoria amazonica is, in fact, a distinct species Victoria boliviana, the world's largest water lily. Discovered in 1837 by John Lindley, it was misidentified when a specimen entered the Kew herbarium in 1845. This reclassification in 2022 highlights its unique characteristics, including its astounding diameter of 3.3 meters, significantly dwarfing an average human, as you can see in the scale analysis. The Victoria boliviana also exhibits a captivating reproductive cycle, a 3-day drama unfolding with remarkable precision. On night 1, the flower is female, undergoing thermogenesis generating heat and a pineapple-like scent to attract beetles. It traps these pollinators for 24 hours. On night 2, a dramatic sex change occurs. The flower transitions to male, releasing the now pollen-coated beetles, which then disperse the pollen. Finally, on day 3, the flower submerges to facilitate seeding. Thermogenesis, the ability to raise its temperature by up to 10 degrees Celsius above ambient air, is crucial for volatilizing its scent and ensuring efficient pollination. This botanical engineering marvel allows a 1 mm thick membrane to support an astonishing 80 kilograms. The geometric rigidity of the Victoria boliviana leaf enables its soft tissue structure to bear dynamic loads equivalent to an adult human. This is achieved through several ingenious design elements. First, a fractal vein system ensures a radial distribution of stress. Second, cross ribs provide lateral stability. Third, air pockets trap gas, providing essential buoyancy. And finally, spines offer defense against predation, protecting this incredible natural structure. Moving from nature to architecture, we see the first significant mimic in history, the Crystal Palace, built in 1851. Joseph Paxton, its designer, famously said, "Nature was the engineer, Paxton was the builder." He directly modeled the cast-iron framework of this monumental exhibition hall on the rib and crossbeam structure of the giant water lily. This direct inspiration allowed for an incredibly strong yet lightweight structure, proving that nature's designs offered powerful solutions to engineering challenges even in the industrial age. So, what exactly is biomimicry? It is innovation inspired by nature, and it can be applied at 3 distinct levels. At the organism level, it's about mimicking form, copying the shape or structure of a specific organism, much like how a leaf's structure can inspire architectural elements. At the behavior level, we mimic process, copying how an organism acts or interacts with its environment, such as a bird's nesting techniques influencing material use. Lastly, at the ecosystem level, we mimic the system, copying how a whole ecosystem functions, for example, designing systems where waste equals food and resources are continuously recycled. When applying biomimicry, we generally follow 2 methodologies. The first is problem-based, or design to biology. Here, we start with a human challenge and look to nature for a solution. A prime example is Daimler Chrysler's bionic car, which found inspiration in the boxfish's skeletal geometry to optimize airflow and achieve a low drag coefficient. The second approach is solution-based, or biology to design. This involves identifying an interesting biological property and then finding a potential use for it. An excellent illustration is self-cleaning paint, inspired by the superhydrophobic microstructure of the lotus leaf, which naturally repels dirt and water. Let's explore another remarkable case study, the Eastgate Center in Zimbabwe, inspired by the ventilation system of a termite mound. Termites maintain a constant 30 degrees Celsius interior temperature in their mounds using a sophisticated natural ventilation system. The Eastgate Center cleverly mimics this stack effect, with central chimneys and subterranean channels that draw in cool air and expel hot air. As a result, this building uses 90% less cooling energy than conventional buildings of its size, a testament to the power of biomimicry in addressing climate control. Our next case study focuses on shading the MMAA office in Qatar, which draws inspiration from the cactus. Cacti have evolved remarkable ways to regulate heat and light through their spines and unique surface properties. The MMAA office translates this into a bioadaptive shading system. Its building skin features automated louvers designed to mimic cactus transpiration and self-shading, dynamically regulating light and heat gain. This responsive solar shading system results in an impressive 40% reduction in thermal efficiency, optimizing comfort and energy use. Another compelling example is the Council House 2, or CH2, in Melbourne, which looks to tree bark and human bronchi for its design. The facade of CH2 acts as a living membrane, adapting to its environment. The west facade mimics tree bark for structural protection and to manage heat absorption and light reflection. Meanwhile, the north and south facades are designed to resemble bronchi, facilitating efficient gas exchange and natural ventilation. This multifaceted approach creates a building that breathes and protects itself, much like an organism. These examples bring us to the adaptive envelope matrix, a framework for dynamic building skins. This matrix helps us think about how buildings can intelligently respond to their environment, much like living organisms. We consider 4 key elements: heat, with the goal of thermal regulation using biostrategies like insulation and mass, applied through thermal mass walls or phase change materials. Light, focusing on solar control through filtration and shading, implemented with dynamic louvers or deep overhangs. Air, aiming for natural ventilation using stack effect and flow, seen in adjustable vents and atriums. And finally, water, with the goal of conservation through collection and recycling, applied via greywater systems and humidity control. This holistic approach leads to truly adaptive and efficient structures. Why must we mimic nature? The urgency of this shift is underscored by the inefficiencies of traditional building designs. Static envelopes contribute to a staggering 23% of global energy consumption and 30% of all electricity use, often leading to issues like sick building syndrome. In contrast, adopting dynamic membranes inspired by biomimicry offers a path to buildings that are adaptive, responsive, and vastly more efficient, fundamentally changing how we interact with our built environment and its impact on the planet. From the Amazonian water lily to the urban metropolis, the lessons are clear. Joseph Paxton's Crystal Palace demonstrated that nature holds structural secrets waiting to be discovered. The intricate designs we've seen, like fractal geometry in the Victoria Boliviana, allow for maximum strength with minimum material. Ultimately, biomimicry moves architecture beyond static boxes, transforming them into living, breathing systems. As Janine Benyus eloquently states, nature has already solved the problems we are facing. We just need to read the blueprints. Here are the sources and further reading that informed this presentation. We encourage you to explore these fascinating articles and research papers to delve deeper into the world of biomimicry and its applications.